The title of my talk is By Resolving Graph Homomorphisms and Application to Symbolic Dynamics. Indeed, I am working on dynamical systems, a branch of mathematics other than combinatorics. In dynamical systems, one wants to study certain dynamical systems, that is, spaces in which projections are given, and also wants to classify homomorphisms between dynamical systems. To settle these questions, a notion of resolving graph homomorphisms has been appeared in the field of symbolic dynamics, a part of dynamical systems. So we are led to consider about graph theory. Now we know that these resolving graph homomorphisms arose under different names in different fields of mathematics. For example, equitable partitions in the theory of spectral graphs, or categorical approach of graph figurations are such an example. So in this talk, we'll concentrate on the existence and the extension property of these resolving homomorphisms. This my presentation is based on the following talks. You can see my papers on the archive. So after presenting some terminology in first section, we'll give some equivalent condition about the existence of resolving and covering homomorphisms in section 1. And in the second section, we'll give some extended results about resolving homomorphisms. And in final section, we'll give some application to symbolic dynamics. So the first two sections are wholly combinatorics. So let's begin with the definition of resolving homomorphism. Let G be a digraph whose vertex set is V and whose edge set is E. For each vertex I in a graph G, we say that let E subscript Ig the set of all outgoing edges from the vertex I. And let G and H be digraphs. A graph homomorphism is just a pair of vertex mapping and an edge mapping such that the adjacency rules are preserved. That is, if E is an edge from a vertex I to J, then P E is an edge from V, Pi to Pj. And we say that graph homomorphism P is line resolving if P restricted to E subscript I is injective for each I. And if we consider the difference direction and if we consider the set of all incoming edges from the vertex I, then we can define similarly the definition. We can define similarly left resolving condition. And we say that a graph homomorphism is bi-resolving if it is left and right resolving. So this is the definition. And we have one example. Suppose the following two graphs are given. This graph is G and this graph is H. When we define the vertex mapping as the subscripting dropping code and label the edge label the edge as follows, then this is a graph homomorphism. Since I1 goes to I and I2 goes to I, and this edge is mapped to this yellow edge, and this mapping clearly preserves the adjacency rules. But this is not a bi-resolving homomorphism. Since consider about this vertex I1 and its image I, then it has two outgoing edges whose labels are same to this edge. So it is not a bi-resolving homomorphism. However, if we change the label of the one edge from I1 to J1, then this is right resolving and it is left resolving. So it is a bi-resolving homomorphism. Now we consider some special kind of resolving homomorphism called covering homomorphism. It is very similar to resolving homomorphism, but it is a special kind of resolving homomorphism. Resolving homomorphism is defined when this map is injective for each vertex I. We say that this homomorphism is light covering when this is a bijective for each vertex I. And we say that P is bi-covering if it is left covering and also right covering. Then this map is bi-resolving, but this is not bi-covering. Since there are no outgoing edges from J1, and image of J1 is J and JS outgoing edges, so it is not a bijection, so it is not bi-covering. However, if we add some edges and vertices to the graphs, then this is bi-covering. So it is an example of bi-covering homomorphism. So we want to characterize when there exists a bi-covering or bi-resolving homomorphism from one graph to another graph. To begin with the sub-amalgamation matrix. Suppose zero matrix is called a sub-amalgamation matrix. It has exactly one in each row. So using this sub-amalgamation matrix, in the middle of 70s, Williams showed that there exists a light covering homomorphisms from G to H, graph G to graph H. If and only if there is a sub-amalgamation matrix satisfying this condition. In this condition, AG and AH means the adjacency matrices of the graph G and H. And in the beginning of 90s, also showed that when there is a bi-covering homomorphism from G to H, then there is a sub-amalgamation matrix satisfying this condition. And he asked that the converse, whether converse are true or not. We show that there is the converse is true. That is, there is a bi-covering homomorphism from graph G to H if and only if there is a sub-amalgamation matrix as satisfying the condition, the following two conditions. So the implication from the left-hand side to right-hand side is well known, and we are concentrating. The hardest part is the implication from the right-hand side to the left-hand side. So I sketch the brief of the proof. Since S is an amalgamation matrix, then we can associate a function to this amalgamation matrix. Since recall that the definition of amalgamation matrix. Amalgamation matrix is a matrix in which each row has exactly one ones. So by defining for each vertex I as PVI, the unique vertex I, satisfying this condition, we can say that PV is a mapping from VG to VH. The vertex mapping from the vertex set of G to vertex set of H. And to apply the inductive argument, we just let G0 equal to G and H0 equal to H. Then it's clear that G0 and H0 satisfies this inductive hypothesis, since it is just the condition guaranteed in the theorem 1. And take, sorry.
What is A n minus 1? H n minus 1?
Yes. A, G, n minus 1 is the adjacency matrix of G, n minus 1. So G0 and H0 are given, and we have, for the case of n is 1, and these matrices are given. So take an edge, take an arbitrary edge from H n minus 1 and let H n the graph in which any other vertices and edges are exactly the same to Hn except one deleted He. Then we can prove by using Hall's theorem and the property of bi-resolving homomorphism, we can delete edges from Gn-1 so that resulting subgraph Gn, which has the same edges and same vertices as Gn-1 except deleted edges, also satisfies this next inductive hypothesis. And so So this third part is the hardest part of the proof. Then we can assign for each deleted edge alpha, we can define P E alpha is equal to E. So by deleting each edge, we can define graph homomorphism, and we can prove that this is just a bi-covering homomorphism from a graph G to graph H. So the idea is the idea is delete one edge and delete the edges in the domain satisfying the inductive hypothesis and mapping all deleted edges to one edge. So this is just the previous slide. We showed that there is an equivalent condition for the existence of bi-covering homomorphism. So now, to generalize this to resolving homomorphisms, consider about the following theorem of Williams. Williams also showed that there is a light resolving homomorphism from G to H if and only if there is some amalgamation matrix satisfying this condition. Note that the equality condition is replaced with this inequality sign. Then, similarly, we can show that there is a bi-resolving graph homomorphism from G to H if and only if there is a sub-amalgamation matrix satisfying the similar condition in which the equality sign is replaced with the inequality sign. Even though bi-covering homomorphism is a special kind of bi-resolving homomorphism, to prove this theorem, the idea is somewhat different. Key lemma is as follows. To show the existence of bi-covering homomorphism, we cut and deleted edge from inductively. However, to show the existence of bi-resolving homomorphisms, we first add some edges and vertices to the original graph G, so that we can construct a enlarged graph G tilde and enlarged amalgamation matrix S tilde satisfying this condition. Then, by using this lemma, we can say that there is by using this lemma and the previous theorem, we can say that there exists a bi-covering homomorphism from graph G tilde to graph H. Then, by definition, the restriction of this graph homomorphism to G is bi-resolving homomorphism. So, this theorem 1 and theorem 2 is a generalization of Williams, and it is the answer of the Close question. So, using these previous theorems and using motivated by the topological covering theory, we consider the extension results about resolving homomorphisms. We define some terminology. Suppose that a homomorphism from G to H is given. Then the multiplicity of a homomorphism denoted by multiplicity of phi is defined by the maximal number of pre-images of vertices and H under the vertex mapping PV. So consider about this example. The vertex mapping is given by the subscript wrapping code, and this H mapping is defined by this label coloring. Then, since vertex I has 3 pre-images and vertex J has 2 pre-images, we can say that multiplicity of homomorphism is 3. This multiplicity is somewhat useful to classify and characterize some property in the bi-covering and bi-resolving homomorphisms. Since, in a topological point of view, a bi-covering homomorphism can be regarded as a covering map between two graphs. In a topological point of view, finding all bi-covering homomorphisms to a graph correspond to finding all covering spaces finding all covering spaces which has finite sheet. This approach has first observed by Gross and Tucker, and motivated by this result, we want to investigate the extension property of by resolving graph homomorphism. So let P be a graph by resolving graph homomorphism. Then we can first show that there exists a bi-covering extension. Bi-covering extension means that G tilde is a graph containing G and P tilde is an extension of P. So there is a bi-covering extension such that multiplicity of extension is equal to the multiplicity of original homomorphism. And when G and H satisfy some nice condition, then so is G tilde. For example, when G and H are strongly connected, then the resulting extension G tilde is also strongly connected, and similarly for weakly connected graphs. So this graph is shown in previous slide. By adding some vertices and edges, we can make by covering homomorphism from the extended graph to the domain, and remaining the multiplicity. To investigate some certain properties in dynamical systems, the strongly connected graph is very useful. So even though G is not strongly connected, we want to find the condition when G tilde can be found with the condition strongly connected or weakly connected. So the natural question is the following. If H is strongly connected, we want to find the condition for the original graph or the original bi-resolving homomorphism, so that we can find a bi-covering extension who has a strongly connected domain. It is not true in general that if G is not strongly connected and H is merely strongly connected, then G tilde can be found so that G tilde is strongly connected. There is an example such that G is just a graph and H is a strongly connected graph, and for any bi-covering extension of the original bi-resolving extension, bi-resolving homomorphism, P tilde cannot be found so that the domain is strongly connected. So we want to find such a condition. And other than many results, we have one main result. Suppose that a bi-resolving graph homomorphism is given and H is strongly connected. When graph G and H are given, then we can find their adjacency matrices and we can compute their spectral radius. So let lambda G and lambda H be spectral radius of their adjacency matrices of graph G and H. Then when spectral radius of G is strictly less than spectral radius of H, then we can show that for any n greater than multiplicity of n, there is a bi-covering extension P tilde from the related domain G tilde to H, such that G tilde is strongly connected and it has multiplicity of arbitrary degree, arbitrary n, which is greater than the multiplicity of phi. These two conditions are crucial. Even though only one condition is removed, then the theorem 4 is not true. So these two conditions are essential. However, this is not an infinity condition, and so we want to find some narrow conditions to guarantee the existence of bi-covering homomorphisms whose domain can be found to be strongly connected. And in theorem 4, we can say that if strongly connected is replaced with weakly connected, the same result holds. So this is the result about bi-covering extension. And in the end, we have some more result about the extension of bi-covering extension, but it is somewhat technical and somewhat artificial. So I'll skip the other results. So in the first section and second section, we defined resolving and covering homomorphisms, and we presented the result about the existence and extension property of resolving homomorphisms. In the final section, we want to apply this result to the extension problems in symbolic dynamics. So the symbolic dynamics is a part of dynamical systems in which a space whose element consists of a space consisting of by infinity sequences of symbols are studied. So there are many approaches to study symbolic dynamics, and in this talk we are concentrated on these approaches. We want to consider about classification problems and extension problems in symbolic dynamics, and we want to use graph theoretic argument. So let's define some element definitions. When a digraph is given, then the edge shift is part of symbolic system, satisfying that xg is the set of all by infinity trips on G. And the shift map is defined by making one symbol to shift to another symbol to the left. So this edge shift and shift map forms a dynamical system, since iteration of shift map becomes a group action, G action. And a sliding block code is a shift commuting continuous map between edge shift that is satisfying the condition. So a sliding block code or a code is merely a generalization of a one-dimensional cellular automaton. So in this definition, we can phrase the extension problem in symbolic dynamics. One of the important problems in symbolic dynamics is about extension problem. That is, when the edge shift x and y are given, and there is a code from x to y, and when there is a edge shift x bar containing x with certain properties, we want to extend phi to a factor code from x bar 1 to y. So if code is defined on a proper subshift of the domain, we want to extend this to a code defined on whole edge shift. However, it is not so easy, and sometimes it is not possible to extend one map to one code to a code which is defined on the whole domain. So we want to consider about this weak version of the extension problem. In this weak version of the extension problem, the setting is the same. P is a code from edge shift x to edge shift y, and phi has certain properties. Then we are allowed to construct an enlarged domain x bar, and to extend phi to a factor code, that is surjective code on x bar, respecting the properties. So there are many results about extension problems, and some extension problems for certain class of edge shifts are proved on the approach of dynamical systems, or proved on the differentiations and so on. We want to give some result about extension problem in this extension problem using the graph theoretic argument explained in the first and second section. So define the by closing homomorphism. A sliding block code from edge shift x to an edge shift y is called a by closing if it is topologically equivalent to a code induced by resolving homomorphism. This is somewhat complicated definition, but consider about the definition of sliding block. Sliding block code is a shift commuting continuous map between edge shift. So when a graph homomorphism is given, then it naturally induces a sliding block code. So it is merely this code induced by resolving homomorphism is merely by resolving graph homomorphism between two graphs. And x and y, since x and y are edge shift, by closing code is topologically equivalent to a code which is equivalent to by resolving homomorphism. Then we can present the following theorem on the extension of sliding block code. Suppose that P is a biclosing code defined as follows. If P is not onto and Y is an irreducible edge shift, that is edge shift defined by strongly connected graph, then the following statement is true. When the maximal cardinality of sliding block code is defined as D, then for each n greater than D, there is a constantly n-tone extension. Now this constantly n-tone code, which is the extension of original sliding block code phi, such that x tilde is an irreducible edge shift, an edge shift defined by strongly connected graph. And furthermore, if x is irreducible, that is, as we have mentioned, x is an edge shift defined by strongly connected graph, then there is also d-tone extension, where x tilde can be chosen to be irreducible edge shift. So we can say that when bi-resolving code is given, then we can change this bi-resolving code to a code which is defined by resolving graph homomorphisms. And we can say that this, by using the approach of symbolic dynamics and by using the extension property or by resolving graph homomorphism to by covering graph homomorphism in previous section, we can show that this by closing code can be extended to by covering homomorphism, or in the sense of symbolic dynamics, constant tone code, and we can give a low bound D, so that when an integer n is greater than D, then there is an n to 1, constantly n-tone extension of this original by closing code. So this is the connection with some graph theoretic argument or by resolving homomorphisms and the result about extension property in symbolic dynamics. This is the end of my talk. Thank you.